In the earliest chapters of the universe, long before galaxies found their shapes and long before stars settled into ordered constellations, something impossible seems to have happened. When astronomers point the most powerful telescopes toward the edge of the observable cosmos, toward light that has traveled for more than 13 billion years, they find shadows that should not exist. Only 400 million years after the Big Bang, when the universe was still young, turbulent, and barely transparent, there were already black holes with masses reaching 1 to 5 billion suns. According to our standard cosmological models, such titans should not have had time to form. Black holes are expected to begin as the remnants of massive stars, tiny seeds of perhaps tens of solar masses, and grow through steady accretion or mergers. But even under the most optimistic assumptions, there simply isn't enough time in those first few 100 million years to reach such staggering scales. It is as if skyscrapers appeared before the invention of bricks, as if fully formed giants walked the earth before the first organisms assembled. These objects, early quasars blazing at the edge of time, behave like cosmic paradoxes, ancient ruins that predate the civilizations that should have built them. Their light, amplified across billions of years, reaches us as a kind of cosmological ghost story, a reminder that the universe is capable of accelerating, bending, or completely ignoring the rules we think we understand. This video begins at that unsettling boundary, where observation defies theory. We will explore what these early monsters might be, how they defied the limits of known physics, and what their existence tells us about the true nature of cosmic evolution. Are they evidence of unknown physical processes, exotic collapse mechanisms, or flaws in our understanding of the infant universe? The question is simple, yet enormous. How did supermassive black holes appear so early, so impossibly early, in the history of everything? Tonight, we follow that question into the darkness. To understand how the earliest supermassive black holes emerged, we must step back into a universe that was barely awake, a cosmos between 100 and 400 million years old. This was a time when the darkness after the Big Bang had only just begun to lift, and the first structures were assembling from chaos. The universe then was radically different from the one we see today, smaller, denser, hotter, and filled only with the simplest ingredients. The matter content was astonishingly pure. There were no metals, no carbon, no oxygen, no iron, none of the familiar building blocks forged in later generations of stars. Instead, the entire cosmic medium consisted almost exclusively of hydrogen and helium, with only trace amounts of lithium. These were the raw materials left behind by primordial nucleosynthesis, and without heavier elements to help cool collapsing clouds, the gas behaved in unusual ways. It remained warm for longer, resisted fragmentation, and tended to collapse into much larger clumps than the cold molecular clouds of the modern universe. During this period, gravity began to gather these pristine gases into the first great reservoirs, enormous protogalactic clouds forming inside the invisible scaffolding of dark matter. The cosmic web was still in its infancy, a foam of filaments and nodes where matter pooled and deepened. Within these pockets, temperatures soared and densities rose as hydrogen spiraled inward. The conditions were extreme and unstable, but they were also fertile. Out of this violent simplicity were born the first stars, the enigmatic Population 3. These stars were unlike anything that exists today, titanic, volatile, and short-lived. Without metals to aid in cooling, the collapsing gas clouds produced stars that were incredibly massive, often ranging from dozens to several hundred times the mass of our Sun. Their cores burned fiercely, igniting thermonuclear reactions that filled the young cosmos with light for the very first time. This era is often called the Cosmic Dawn, a transition from a universe ruled by darkness to one ruled by radiation. The environment of the early universe was not just capable of creating giants, it practically demanded them. The density of matter was high enough that gravitational collapse happened rapidly. The absence of metals forced star formation toward larger scales. And the turbulent, unstructured cosmic gas made it possible for massive objects, whether stars or gas clouds, to form and evolve faster than in any later epoch. This was the perfect nursery for extreme phenomena. And somewhere inside these overgrown structures, whether through the collapse of supermassive stars, the direct collapse of enormous gas clouds, or the runaway growth of dense nuclear clusters, the seeds of the earliest black holes began to form. These first beacons of gravity emerged not in a quiet, stable cosmos, but in a universe that was raw, hot, and violently creative. A universe that had the unique ability to produce monsters. If the early universe truly contained black holes weighing 1 billion suns, then we face a profound contradiction. According to every physical model we have, there simply wasn't enough time for them to grow. Black holes do not expand explosively or instantly. They grow slowly, through a painstaking process governed by the laws of gravity, radiation, and angular momentum. And those laws impose strict limits on how quickly a black hole can feed. The standard growth path begins with a seed, a black hole left behind by the collapse of a massive star, typically no more than 30 to 100 solar masses. From there, the only two mechanisms available are gas accretion and mergers with other black holes. Mergers can boost mass in irregular jumps, but they are too rare in the early universe to explain billion solar mass monsters. That leaves accretion, the slow and steady intake of gas spiraling into the black hole's gravitational well. But accretion is not a free-for-all. As gas heats up and compresses near the event horizon, it emits radiation, sometimes an enormous amount of it. That radiation pushes back on the infalling gas, creating a natural choke point, the Eddington limit. This limit defines the maximum rate at which a black hole can grow without blowing away the material it is trying to consume. The brighter the accretion flow becomes, the harder it becomes for new gas to fall inward. It is an elegant self-regulation mechanism written into the fabric of astrophysics. Under steady Eddington limited accretion, a black hole doubles its mass roughly every 45 million years. This may sound fast, but cosmic history is unforgiving. To grow from a typical stellar seed, say 100 solar masses, to the size of the earliest quasars, 1 to 5 billion solar masses, a black hole would need dozens of doubling cycles. Even in the most optimistic scenario, this mass amplification requires over 800 million years of uninterrupted, perfectly efficient feeding. And that assumes several unrealistic conditions: that gas is always available, always cool enough to fall inward, and never blown away by radiation, turbulence, or feedback from star formation. But the quasars discovered by JWST and previous surveys appear only 400 million years after the Big Bang. They are simply too big for that time frame. Even if their seeds were unusually large, 10,000 or even 100,000 solar masses, the growth timescales still overshoot what early cosmic history allows. Something does not add up. This is the core of the puzzle. Supermassive black holes seem to have grown faster than the universe allowed. By the rules we know, they could not have reached such colossal masses so soon. And this contradiction forces us to question our assumptions about the origins of the very first black holes, about the nature of accretion, and perhaps even about the physics of the early universe itself. The problem of time is therefore not a minor hiccup. It is the heart of the mystery. It tells us that the earliest black holes were not just massive. They were impossible. If the idea of billion solar mass black holes existing only a few 100 million years after the Big Bang sounds extreme, the situation becomes even more unsettling when we turn to the actual observations. These are not theoretical constructs or speculative objects. They are real quasars, bright, distant, and shockingly massive, whose light reaches us from an era when the universe was still in its infancy. When astronomers study the cosmos at redshifts Z almost equal to 6 to 7, they are essentially looking back more than 13 billion years, to a time when galaxies were only beginning to assemble. Yet in this primordial landscape, we find quasars powered by black holes of nearly unimaginable size. The most famous among them is Ulysses J1342 plus 0928, a quasar whose light began its journey when the universe was just 690 million years old. Its central black hole weighs about 800 million solar masses, already far beyond what our models predict for such an early epoch. Another extraordinary example is SDSS J0100 plus 2802, a quasar observed at high redshift with a black hole mass of roughly 12 billion solar masses. Even in the modern universe, such a mass is staggering. But to find an object like this when the cosmos was still young is nothing short of a cosmological shock. These objects force us to confront the possibility that the earliest black holes were not following the rules we thought applied to all of them. But how do we know the masses of these distant giants? Astronomers rely on a combination of spectral signatures and physical models. The gas swirling around a black hole, the accretion disk, emits intense radiation as it heats to millions of degrees. This radiation ionizes gas clouds farther out, creating broad emission lines in the quasar's spectrum. The width of these lines reveals how fast the gas is moving. The faster the motion, the stronger the gravitational pull, and therefore the larger the mass of the black hole. By combining these measurements with the luminosity of the quasar, astronomers obtain reliable mass estimates, even across billions of light years. What makes these early quasars anomalous is not just their size, but the speed at which they must have formed. Their existence requires either an extreme departure from Eddington-limited growth, an entirely new class of massive seed black holes, or a mechanism in the early universe capable of bypassing the slow, steady accretion process altogether. In every case, the implication is the same. The standard black hole formation story does not explain what we see. These quasars stand like cosmic monuments at the edge of time, observational proof that something extraordinary was happening in the first billion years of the universe. They are not theoretical puzzles. They are hard data, and they demand answers. One of the leading explanations for the existence of early supermassive black holes bypasses the traditional path of stellar evolution altogether. Instead of beginning with a massive star that collapses into a small seed, this scenario proposes something far more dramatic: an entire gigantic cloud of primordial gas collapsing directly into a black hole. No star is formed. No supernova erupts. Gravity simply overwhelms every opposing force, and the cloud falls inward until a massive black hole is born in a single catastrophic event. This mechanism, known as direct collapse, produces black hole seeds that are astonishingly large from the very beginning, on the order of 10 to 10 solar masses. Such a seed skips the slow, uncertain early stages of black hole growth. Instead of starting as a tiny remnant of a dying star, it begins its existence already enormous, with enough mass to reach 1 billion suns within the first few 100 million years of cosmic history. For direct collapse to occur, however, the conditions must be exceptionally specific. The cloud must remain hot and unable to fragment, which is only possible if it cannot cool effectively. In the early universe, the primary coolant of primordial gas was molecular hydrogen, but this fragile molecule can be easily destroyed by intense ultraviolet radiation from nearby population 3 stars or early protogalaxies. A strong UV background prevents the cloud from cooling, forcing it to remain warm and massive, perfect for direct collapse. Another requirement is extremely low angular momentum. If the cloud is rotating too fast, even slightly, centrifugal forces will support it against collapse, causing it to fragment into stars instead of falling inward smoothly. The environment must therefore either naturally suppress rotation or redistribute angular momentum through turbulence, mergers, or gravitational torques. Finally, the gas cloud must avoid early star formation entirely. If even a few stars form, they will inject heat, radiation, and metals into the cloud, disrupting the delicate balance required for direct collapse. That is why this scenario is most plausible in pristine regions of the early universe, areas untouched by the chemical enrichment that came later. Despite these strict conditions, many cosmologists consider direct collapse the most promising explanation for the earliest supermassive black holes. It produces massive seeds quickly, naturally bypasses the limitations of Eddington growth, and aligns with simulations showing that such environments could indeed occur during the first 300 million years. It does not require exotic physics, only a special combination of natural processes working together at the right moment. If direct collapse happened even a handful of times across the early cosmos, it would be enough to explain the ancient quasars we see today. Massive seeds born whole, without the long wait for stars to live and die. Giants formed from the raw, untouched hydrogen of the universe's youth. Another pathway toward the formation of early black hole giants begins with the first generation of stars themselves, population 3, the metal-free titans of the young universe. These stars, formed from pristine hydrogen and helium, lived in an environment unlike anything that exists today. Without metals to efficiently cool collapsing gas, the earliest stellar nurseries produced stars of extraordinary size, sometimes reaching 200, 300, or even more solar masses. They were luminous, unstable, and short-lived, and their existence may have provided the seeds for the first black holes. The physics is straightforward. Stars this massive exhaust their nuclear fuel in just a few million years. When their cores can no longer support the crushing weight of their outer layers, they collapse catastrophically. Instead of a typical supernova leaving behind a neutron star or a modest black hole, these giants produce direct stellar collapses that generate black holes of roughly 100 to 300 solar masses, far larger than anything produced by modern stellar evolution. This scenario is appealing because it does not require exotic physics or extreme cosmic coincidences. The formation of supermassive population 3 stars is a natural consequence of the early universe's simplicity. With no metals present, gas clouds cannot radiate heat efficiently, meaning they remain warm, resist fragmentation, and collapse into fewer but far more massive clumps. These clumps become oversized protostars, which grow through rapid accretion and mergers, quickly ballooning into luminous monsters. But even though population 3 remnants provide larger seeds than normal stars, they still face a crushing obstacle, the problem of time. Starting with a seed of 200 to 300 solar masses is better than starting with 30, but it is nowhere near enough to reach 1 billion solar masses in less than 400 million years. Even if such a seed grew continuously at the Eddington limit, it would need well over 500 million years to reach the sizes we observe in the earliest quasars. In reality, accretion is rarely continuous, gas is often disrupted, and early galaxies are chaotic, turbulent environments that make efficient feeding extremely difficult. Population 3 seeds are therefore too small and too slow. They help close part of the gap, but not enough to solve the mystery. There simply isn't enough time for stellar collapse seeds, no matter how large, to evolve into the 1 to 5 billion solar mass black holes detected at redshift 6 and beyond. These early quasars seem to demand seeds thousands of times larger from the start. This does not diminish the importance of population 3 stars. They were the universe's first forges, enriching space with heavy elements and shaping the conditions for later cosmic evolution. But as the primary explanation for early supermassive black holes, they fall short. Their seeds are impressive, but not impressive enough. The conclusion is unavoidable. Population 3 stars could light the first fires of the universe, but they cannot alone explain the earliest cosmic monsters. A third possibility challenges one of the most fundamental assumptions in black hole physics: the Eddington limit, the theoretical maximum rate at which a black hole can steadily consume matter. Under ordinary conditions, as gas falls inward, it heats up and emits radiation. That outgoing light produces pressure that pushes incoming gas away. This delicate balance caps the feeding rate and normally prevents a black hole from growing too fast. But what if the early universe wasn't ordinary at all? What if black holes back then could eat faster than physics today would allow? The early cosmos was chaotic and violent. Galaxies were small, turbulent, and rich in dense, cold gas. Instead of organized disks and stable structures, young black holes found themselves surrounded by clouds collapsing from all directions, forming thick, unstable accretion flows. In such environments, radiation pressure may not have been able to push gas away effectively. Gas could have plunged inward through narrow channels or dense streams, giving the black hole a temporary loophole to exceed the traditional Eddington limit. This idea, super Eddington accretion, proposes that young black holes may have undergone short but extremely intense growth episodes, swallowing matter many times faster than modern theory predicts. Instead of a gentle, balanced inflow, the accretion disk may have been puffed up, turbulent, and full of dense clumps that could fall inward before radiation pressure had time to stop them. Some simulations suggest that, under these extreme conditions, infall occurs through funnel-shaped streams where radiation escapes in specific directions while matter rushes inward from others. The black hole, in effect, cheats the limit by letting light leak out but still consuming far more material than expected. If these phases lasted long enough, tens of millions of years rather than a few thousand, they could dramatically accelerate growth. A black hole starting with only a few hundred solar masses could, in principle, reach millions or even tens of millions of solar masses far faster than standard accretion models allow. Yet even this scenario faces its own uncertainties. The biggest question is stability. Can these wild, turbulent flows persist, or do they collapse into ordinary Eddington-limited disks after only brief flares? And if they do persist, can they maintain the extreme feeding rate needed to produce billion solar mass quasars in under 400 million years? Super Eddington accretion doesn't solve everything, but it narrows the gap. It suggests that the early universe may have operated under a different set of practical limits than the calm, organized galaxies we see today. Instead of slow, orderly growth, the first black holes may have experienced frantic feeding frenzies, devouring entire clouds in a single gravitational storm. In this interpretation, the earliest black holes were not just seeds, they were opportunists. They grew by exploiting the chaos of the infant cosmos, eating in great gulps whenever the turbulent environment allowed it. Whether this alone can produce the 1 to 5 billion solar mass monsters seen at redshift 7 remains debated, but super Eddington episodes remain one of the most provocative possibilities. Another leading explanation for the existence of impossibly massive black holes so early in cosmic history is rooted not in how fast they grew individually, but how often they collided. In the infant universe, between 200 and 600 million years after the Big Bang, galaxies were nothing like the majestic spirals and calm ellipticals we see today. They were tiny, turbulent, and unimaginably dense. These first proto-galaxies packed enormous amounts of gas, stars, and dark matter into regions only a fraction of the size of modern galaxies. In such extreme environments, encounters were not rare exceptions, they were the rule. Stars orbited close together, often separated by distances smaller than the space between planets in our solar system. Many of these stars were massive and short-lived, ending their lives in core collapse and leaving behind stellar mass black holes. With so many stars dying so quickly and in such close proximity, these early galaxies may have been black hole factories, producing dozens or even hundreds of small black holes within a short cosmic window. And in these crowded, chaotic systems, gravitational interactions constantly perturbed their orbits, driving black holes toward one another. When two black holes pass close enough, they can become gravitationally bound, losing orbital energy through gravitational radiation and spiraling inward until they merge. In the modern universe, such events are rare and dramatic, but in young protogalaxies, where densities were thousands of times higher, these mergers may have happened continuously, building up mass step by step. A black hole of 30 solar masses merges with another 30 solar mass remnant, then with a 100 solar mass remnant, then with something larger still. Over time, this runaway chain of coalescences could produce black holes of tens of thousands, hundreds of thousands, or even millions of solar masses, far faster than accretion-driven growth alone would allow. In this scenario, early galaxies act as merger engines, rapidly assembling the seeds that would later evolve into the billion solar mass behemoths powering the earliest quasars. Instead of slow, steady feeding, the black holes grew by violent leaps, each merger injecting enormous gravitational energy into the surroundings and sending out ripples in space-time. These ripples, known today as gravitational waves, are one of the strongest clues that this process may indeed have happened. Modern detectors like LIGO and Virgo have already observed dozens of black hole mergers, proving that such events are common and energetically powerful. Though we cannot yet observe mergers from the early universe directly, the patterns and masses we detect today hint at an earlier epoch when such interactions were far more frequent. If protogalaxies truly were dense gravitational arenas filled with unstable orbits and young black holes, then mergers may have been a dominant growth mechanism. A single black hole forming from the collapse of a massive population 3 star could, through a chain of rapid collisions, jump to thousands of solar masses in a relatively short time. This hierarchical merging effectively bypasses the timing problem. Black holes don't need to accrete impossibly fast. They only need to find each other, which early galaxies made almost inevitable. In this view, the first massive black holes were not solitary monsters growing in isolation. They were the products of cosmic overcrowding, galaxies so compact and dynamic that gravity constantly pushed their contents together until only the most massive objects survived. Among all explanations for the existence of enormous black holes in the infant universe, none is more exotic or more intriguing than the idea that some black holes were not formed from stars at all. Instead, they may have been born before stars existed, forged in the first fractions of a second after the Big Bang. These hypothetical objects, known as primordial black holes, belong to a realm where cosmology, quantum physics, and gravitational theory all overlap. And if they are real, they could solve one of the greatest mysteries in modern astronomy: how billion solar mass black holes appeared so impossibly early. The idea arises from the extreme conditions of the early universe. During the very first moments, long before atoms, light, or even stable particles formed, the cosmos was governed by wild fluctuations in density. Quantum mechanics ensured that different regions of space had slightly different energy levels, and as the universe expanded and cooled, these differences were stretched and amplified by cosmic inflation. If some regions became dense enough, gravity could overwhelm pressure forces and cause the collapse of those tiny patches of space into black holes. Unlike stellar black holes, which can only form from the collapse of massive stars, primordial black holes could form with nearly any mass, from microscopic scales to the mass of mountains, planets, or even stars. In this hypothesis, the first seeds of supermassive black holes did not have to start small. Instead of beginning at 100 or 300 solar masses, As would be expected from population 3-star remnants, primordial black holes could have been born with masses of thousands or millions of suns. If such massive seeds existed immediately after the Big Bang, they would have had hundreds of millions of years to accrete gas, merge with other black holes, and grow into the early quasars we observe. This makes the primordial black hole hypothesis uniquely powerful. It bypasses the timing problem altogether by starting from a head start that nature itself provided. The arguments in favor of this idea are compelling. First, primordial black holes could naturally explain why some quasars at redshifts 6 to 7 appear far too massive for their age. Second, if primordial black holes formed across a wide range of masses, they may also account for some or all of the mysterious dark matter, the invisible substance that shapes galaxies on large scales. Third, gravitational wave observations from LIGO show black hole mergers involving unusually heavy stellar mass black holes, which some theorists interpret as potential indirect hints of a primordial population. But the hypothesis faces significant challenges. Despite decades of searching, astronomers have found no direct evidence of primordial black holes. Many mass ranges have already been ruled out by gravitational lensing studies, cosmic microwave background measurements, and the distribution of galaxies. If primordial black holes existed in large numbers, they would leave fingerprints on cosmic structures that we have not observed. Moreover, the conditions required for their formation, extreme density spikes during inflation, depend on physics we don't yet fully understand. Still, the possibility remains open, especially in specific mass ranges. And because primordial black holes would have existed from the first instant of cosmic time, even a small population could have played an enormous role in shaping the early universe. They may have ignited the first galaxies, triggered early star formation, and served as the initial gravitational anchors around which large cosmic structures assembled. If they were the first black holes, then the earliest quasars are not anomalies, they are simply the descendants of a much older, deeper cosmic lineage. In this sense, primordial black holes offer not just an explanation, but a vision of a universe where gravity began sculpting structure long before the first light ever shone, a universe where some of the oldest objects are so dark that we cannot see them, yet so powerful that they shaped everything we eventually came to observe. The launch of the James Webb Space Telescope opened a new window into the early universe, one sharper, deeper, and more revealing than any instrument before it. And almost immediately, JWST began sending back results that stunned astronomers. Instead of confirming the predictions of the standard cosmological model, it uncovered a cosmos that looked too mature, too structured, and too massive far too early. Among the most surprising discoveries are supermassive black holes and galaxies that appear impossibly ancient, forcing scientists to reconsider some of their most foundational assumptions. One of JWST's most striking findings is the detection of black holes that grew far larger and far faster than any conventional model allows. Observations show quasars and active galactic nuclei at redshifts 10 to 13, epochs less than 300 million years after the Big Bang, hosting black holes with masses reaching hundreds of millions of suns. These objects exist at a time when the universe should still be in its earliest stages of assembling gas clouds. Instead, JWST reveals them blazing with intense radiation, powered by black holes that should not yet exist. Every new dataset seems to uncover even more extreme examples, pushing the timeline further back with each observation. Equally puzzling are the galaxies themselves. JWST has discovered compact, massive galaxies, some with stellar masses rivaling the modern Milky Way, appearing just 500 to 700 million years after cosmic dawn. According to standard cosmology, such galaxies should not have had enough time to accumulate that much mass. Their stars appear old, their structures surprisingly complex, and their densities far higher than expected. These early galaxies are not the small, irregular systems theories had predicted, but instead look like mature, overdeveloped cities appearing in a universe that should still be a wilderness. The combined effect of these discoveries is profound. The early universe appears to have evolved much faster than our models allow. This mismatch suggests that something fundamental may be missing from our understanding. Maybe early gas collapsed more efficiently, maybe black holes grew through unconventional pathways, maybe dark matter behaved differently, or perhaps the seeds of structure were laid down before the first stars formed. JWST does not simply provide images, it challenges the scaffolding of cosmology itself. As the telescope continues to peer deeper, each new dataset adds weight to the idea that the early universe was far more dynamic, far more energetic, and far more surprising than we anticipated. What we once believed to be a smooth, slow buildup now looks more like a sudden ignition, structures appearing too quickly to be easily explained. JWST is not just observing the distant past, it is rewriting the story of cosmic beginnings. And as more observations accumulate, the question grows louder. Was our understanding of the first billion years of cosmic history incomplete all along? Understanding the origin of the first black holes is far more than a niche cosmological puzzle. It reaches into the very foundations of how the universe formed, evolved, and became the place we observe today. These ancient giants were not passive relics of early times. They were active engines shaping the newborn cosmos. If we can uncover how the first supermassive black holes came into existence, we simultaneously uncover how the first galaxies formed, how early gas cooled, how stars ignited, and how structure emerged from primordial darkness. Supermassive black holes influence everything around them. Even in the early universe, their intense radiation, jets, and accretion flows regulated the pace of star formation in their host galaxies. If these black holes were already enormous just a few 100 million years after the Big Bang, it means they must have played a major role in sculpting the earliest generations of stars. Their energy could have heated surrounding gas, prevented runaway collapse, or, paradoxically, triggered star formation in turbulent environments. Understanding their birth is not just about black holes themselves, it is about decoding the blueprint of cosmic architecture. This puzzle also tests the validity of our entire cosmological framework. The Standard Model predicts how fast structures can grow, how quickly matter can collapse, and how long it takes for stars and galaxies to form. Yet JWST observations show objects that seem too massive, too developed, and too luminous for their age. If these early black holes truly defy growth limits, we may be missing key physics, exotic collapse mechanisms, unusual dark matter behavior, or unknown processes in the primordial plasma. The importance of this mystery is profound. It forces us to ask whether our understanding of gravity, structure formation, and early cosmic evolution is complete, or whether the universe still hides a chapter we have not yet read. The first black holes are not just historical curiosities. They may be the Rosetta Stone for interpreting the first billion years of cosmic history. Solve them, and we may solve the origins of galaxies, stars, and the large-scale structure of everything we see. In the end, the mystery of the first supermassive black hole stands like a monument in the early cosmos, silent, ancient, and impossibly large. These titanic objects are not merely remnants of violent processes. They are the oldest architects of structure, shaping the flow of matter long before galaxies settled into familiar forms. Their existence in the infant universe challenges every assumption we hold about how quickly gravity can gather mass, how stars evolve, and how the fabric of space-time behaves under extreme conditions. They rise from the darkness as the first great sculptors of cosmic history. Their early appearance remains one of the greatest puzzles of modern physics. Standard theories tell us the universe did not have enough time to grow such giants, yet there they are, burning like cosmic beacons at the edge of visibility, older than theory allows. Each new discovery widens the gap between what we expect and what we observe. These ancient black holes whisper that our understanding of gravity, matter, and cosmic evolution may be incomplete, that the early universe was far stranger and more dynamic than we ever imagined. They force us to confront the limits of our models and the possibility that new physics lies just beyond the horizon. And yet, there is poetry in this darkness. The deeper we peer into the past, the older the shadows become, stretching far beyond the reach of our theories. These first monsters are not merely anomalies, they are clues, fragments of a forgotten chapter in the story of creation. Perhaps, hidden in their silent glow, lies the truth about how the universe was born, how its first structures rose, and how chaos became the cosmic order we now inhabit. They remind us that the greatest truths may still sleep in the earliest light, waiting for us to understand.